Okay, welcome back. This is our final recording for this year. We will be finishing up conservation of momentum. You have seen conservation of momentum before. You've seen it certainly in chemistry. You've probably seen it in middle school and grade school and like some sort of physical science course that you have. So you are familiar with it. Um, we're at the point now where we will be finishing up today the introduction to physics. We've covered all the intro stuff. Would that we had those couple weeks back that the CPS took from us to get us out early. And we could have taken what we've learned through today and extended it to um, more realistic type problems where things change in the middle. But maybe I'll bring that up towards the end of today. So again, today is the last meeting that we'll be having. Just as a quick review of what we did last time. We did the work energy theorem last time. And again, I introduced that from the idea of conservation of total energy. This work energy theorem actually is more basic. That the work energy theorem can be proven from basic physics that we've had. We need to use calculus, but we're able to prove that. From this, we get conservation of energy, and I'll flip it today and show you where that comes from. But just as a quick example of what we did last week, suppose that you have a 2 kilogram wooden block starting from rest at the top of a ramp. The ramp itself, we don't know about the angle, but the ramp itself is 1 meter high. When it gets down to the bottom, it has a speed of 2.5 meters per second. And the question is, what is the work that is done? I got two screens here that I'm looking at. What is the work done when the block gets to the work done by friction on the block as it slides down the ramp? Okay, so where do we go from here? Well, oops, I need to gain control over this. From time to time, I might have to stop this to get control over this thing properly from the present slide. There we go. Okay. Here's the work energy theorem here. The net work is equal to the change in kinetic energy. The change in kinetic energy is obvious. It's the final kinetic energy, 1/2 mv squared final, minus the initial kinetic energy. The net work is the work done by all the external forces. You can include the internal forces if you'd like, but if it's internal to the system, again, remember what a system is, right? It's everything that is being acted on. We decide what the system is, but in this case, the system would be the block. If we were talking about two objects, like two cars colliding, internal forces here would cancel. We can calculate the work done by the internal forces, but because they are action-reaction pairs, they would cancel in pairs as a network. So the only forces we need to worry about are the external forces, and here we have three external forces acting. We have the work done by gravity, not to forget all the things that we have been doing all year long. We have the free body diagram. We have the force of gravity acting downwards. We have the normal force, the force acting by the surface to keep it from going through the surface, and we have friction, which is opposing the motion as it goes down the ramp. Okay, those three forces. So those three forces can do three separate works. Okay, now we're looking for the work done by friction. The work done by friction. Remember what a work done by a force is, right? A work done by a force F is F d cosine theta. Here it's particularly easy. We don't know what the angle is, so we're not going to be able to find the normal force straight away. This happens to be a straight ramp, so if we didn't know the normal force, we could calculate the work done by friction relatively easily if we knew the coefficient of friction. But even if it wasn't a straight ramp, as I showed you last time, climbing a mountain, the normal force is changing constantly, everything's changing constantly. Finding the work done by friction is a near impossible task. But what we do know is we can apply our knowledge of these two the work done by these two forces, along with the information that we have about the final and initial kinetic energies. Okay. Well, first of all, the final kinetic energy is 1/2 times the mass, which is 2, times the final speed, which is 2.5, which gets squared. And the initial kinetic energy is 0, because it's not moving. Okay. The work done by the normal force is 0, because the work done by the normal force is always 0. The normal force is in this direction. The motion is in this direction. It's perpendicular. Cosine 90 degrees is 0. And the work done by gravity, we already know that. That's going to be mgh, the height. Okay, so mgh plus 0 plus the work done by friction is going to be equal to this right-hand side. M is 2, G is 10, H is 1, plus 0, plus the work done by friction is going to be equal to, what's that number, 6.25. And if you're just simply solving for the work done by friction, the work done by friction is going to be negative, first of all. We've seen that way back when. The work done by friction is always negative. 193.75 joules. Okay. This here is 200. Okay. And you know, the work done by friction, if there was no friction, then the kinetic energy would have to be at the bottom, would have to be 200 joules. Okay. But work does a whole bunch of work here. Right. It steals the vast majority of the work that was done by gravity, leaving only 6.25 for the kinetic energy of motion. Okay, so that's just a quick review of what we did last time. It would be, oops. Okay, let's talk a little bit about what we have actually just done. Okay, let's mouse down. Okay, let me sort of pause this for a second. Yeah, sorry about that. I have to get control over this. Sometimes it doesn't want to respond the way I'm expecting it to. Let's look at this expression a little bit more closely. Right, this is what we had started with. There's two ways of classifying a force. Okay, we can classify a force as a conservative force or a non-conservative force. That's not to say good and evil or Democrat and Republican, but we have a conservative force and a non-conservative force. Okay, what is a conservative force? A conservative force is a when the work is done by conservative force, then that work is independent of the path taken. Okay. For example, gravity. I mean, the work done by gravity doesn't matter how if I take this pen and I pick it up from the floor and put it onto a table, it doesn't matter what the path is, right? It's just simply going to be mgh, right? It's going to be positive if it's moving down, negative if it's moving up. Okay, but it's independent of the paths changed. Okay. Under that condition, if we have a conservative force, then we can talk about the potential energy, right? MGH, that's what potential energy is, right? Potential energy due to gravity is MGH. That was just sort of given to you. You took it for granted as fact. That's where it comes from. Okay, so the potential energy is the negative work done by a conservative force. You don't really need to know that. I'm just sort of you don't necessarily be able to recall that, but when we're using conservation of energy, it's just nice to know where potential energy is coming from. Why we can talk about potential energy sometimes and not potential energy at other times, and it depends on the force that we're talking about. So gravity is a conservative force. So instead of talking about the work done by gravity, we can simply talk about the potential energy that's associated with the position of the object. Okay, and the potential energy is simply the negative work done by that, in this case, gravity. Then we can have a non-conservative force. A non-conservative force is a force that does depend on the path that you take. Okay, if you take the Oops, I got stuck there. Okay, it depends on the path that it takes. For instance, friction, right? If we have friction always opposes the motion. So if we have let me sort of draw it on here a little bit. If we have an object here, and we start here and ready, set, go, start, stop, it's still at the same place. It hasn't gone any place. The work done by friction is 0. If we start and go around in a small circle, then the work done by friction would be the force of friction times the distance, which would be 2 pi r, right? Where r is this distance. If we go in a bigger circle, the r is going to be larger, therefore the distance is larger, and therefore the work done by friction is larger. So that just shows you that the work depends on the actual path taken. Okay, in that case, the work you cannot talk about a potential energy. There is no potential energy of friction. Right? It's a case by case individual calculation that you would have to do. Okay. So there are a number of different conservative forces. For example, gravity that you know, spring forces generally would be conservative. Electromagnetic forces are conservative. There's plenty of most of the forces, all the fundamental forces that you know are conservative, but there's a lot of forces that are conservative. Then there's non-conservative forces. The biggest one would be friction, for instance. A chemical explosion would be a non-conservative force. Where that energy come from? It came from the chemical bonds that are releasing their energy. Okay, so we can talk about conservative and non-conservative forces. Okay, all right. So very, very quickly. Let me get this back on track here. All right, so conservative forces, as a really quick review of what I just said, conservative force is defined in terms of the work done, and the work is independent of the path, all right? We talk about potential energy. As I put an example here, you pick up a book from the floor and you put it on top of the table. The work does not depend on how the book actually got there. It depends only on where it started and where it ended. Same thing with potential energy, right? Potential energy depends only on where you start and where you end. Okay, but a non-conservative force depends on the path that's actually taken. So we can't talk about potential energy. Just to make a connection to what you've done before. When we did momentum, we talked about elastic versus inelastic collisions, right? And in an elastic collision, kinetic energy was conserved, and that's because in an elastic collision, we're talking about conservative forces. We're talking about forces, say, like a piece of paper. I remember Mr. Starita had done this, right? You take a piece of paper and sort of bend it, right? There's no permanent deformation there. I can get that energy back. I can bend this as much as I want, and I can get that energy back. Okay, so that bending is a conservative force. There's no energy loss there. The energy is stored as potential energy, and I can get it back. However, if I take it and crunch it, I ain't getting that energy back. That would be a non-conservative force. That would be an example of an inelastic collision. Remember, inelastic collision, energy is either gained or lost. Okay, something like this, you've lost energy, right? It's gone into deformation. You can't get that back. You can gain energy by having an explosion. Like two cars, you've run into a tanker truck, and a tanker truck explodes, right? All of a sudden, you got this enormous amount of chemical energy that's released. Okay. All right. So how does this come back to conservation of energy? Depending on whether you have conservative forces or non-conservative forces, we can talk about different kinds of conservation laws. The first one is the conservation of mechanical energy. Conservation of mechanical energy is sometimes valid, right? It's valid if there are no non-conservative forces acting. In other words, no friction. So if you see a problem that says there's no friction, then you can use conservation of mechanical energy. Mechanical energy is a combination of kinetic energy or potential energy. right? So as you see here, it's PEA plus KEA equals PEB plus KEB. A and B are 2 points, right? The initial and final, the initial, the middle, the final, whatever two you're comparing, right? You always have you have 2 points that you compare. We've always just compared 2 points, right? Beginning and the end. Usually, we can have a beginning, a middle, and an end, so we can have 2 comparisons, right? But this is conservation of mechanical energy. Conservation of mechanical energy is valid generally for you guys when there is no friction, okay, or nothing is pumping energy in, like there's no motor attached to it pulling it along. You're not pushing it to make it go faster and faster. Okay, so basically, if there is no friction, or if it says there's a non-conservative force acting, then you can. If there is no non-conservative forces acting, then you can use mechanical energy, right? And the other is conservation of total energy. Conservation of total energy is always, 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 always valid. Okay, the difference, if you notice the difference between what you see here and what you see here, is the energy input. Oops, is the energy input and the energy lost. Remember, what's the difference really here is here when we talked about the network. The forces acting in this case were conservative. So instead of talking about the network, we could talk about potential energy. Okay. In this case, in the case of conservation of total energy, the network can be partially potential energy for the conservative forces and partially non-conservative forces, the non-conservative work done by non-conservative forces. We can't write down a potential energy, and that's what these guys amount to. This would be the energy lost to friction, for instance. Right now, the energy lost to friction is inherently a negative number. What I've drawn here is a positive number, so energy loss. So what I'm doing here is like I'm losing energy on this side, I'm adding energy on this side. It's like balancing a checkbook, although you guys don't know how to balance checkbooks. But if you're going to be an accountant, you have to add up all the pluses and add up all the minuses. They're in separate columns, essentially. So this is the energy that is being lost, right? You start out with a certain amount of energy. You might put energy in, you might take energy out. Like this would be the the kernel is the same for the two. All right, but because of the non-conservative forces that are possibly acting, this would be energy that's putting in from like an explosion or motor pushing something along, you pushing something along, and this generally is energy lost due to friction. Okay. Oops, let me clear that, and it's going to say the same what I just said. All right, so energy loss is typically frictional losses, but the energy could also be, for example, a motor pulling a roller coaster up to the top of a ramp, for instance. Okay, all right, so let us try an example. Oops, we just did this. Okay, conservation of mechanical energy example problem. All right, suppose that for the following roller coaster, there is no friction. Okay, so because there's no friction, we can use conservation of mechanical energy. Right, so wonderfully cool. I spent hours drawing this thing, by the way. Here is the procedure that one would follow. I mean, we haven't had a procedure yet for this, so here's your procedure for these types of problems. Okay, first of all, we're talking about the energy at 2 separate points. So we have to get the energy down at the different points, right? We have 4 points here, W, X, Y, and Z. I stole this from someplace, obviously. We're only going to be using W, X, and Y for obvious reasons, because W is where you start, and X happens to be at the ground, right? And Y is 20 meters above the ground. The procedure is to, at each of these points, at W, at X, at Y, at Z, at each of those points, you simply write down the potential and kinetic energy values, right? You can write down the potential energy at W. You can write down the formula, mgh, put the numbers in, 150, the mass of the roller coaster is 150, g is 10, 9.8, and the height is 50, right? And put that all together, you get 75,000 joules for the potential energy at that height. The kinetic energy, since it starts from rest, is 0. At x, we have the potential energy is 0 because it's at the ground, right? We're taking the 0 potential energy to be from the ground. The kinetic energy is 1/2 mv squared, right? That should be a superscript there, all right? So it's 1/2 times 150 times v squared. And we can do the same thing at y, right? We got some sort of combination here. We have both potential. Here we only have potential energy. Here we have only kinetic energy. Here we have both. Okay. So we have potential energy is mgh. H here is 20 meters. So we end up with 30,000 joules, and the kinetic energy is also going to be 75 v squared. Obviously, the velocities here are going to be different. As you go down, the velocity goes up. As you go up, the velocity goes down. So. All right, so here is the question. I have to move this out of the way so I can see what that actually says. All right, find the kinetic energy at the point X, okay? We're using conservation of mechanical energy. So basically, this box is set equal to this box, okay? If I can, where's my annotation bar? There it is. Mouse. All right. So basically, what we do is we take this box and set it equal to that box. 75,000 plus 0. 75,000 plus 0 is equal to 0 plus kinetic energy. Do not make the mistake, please. All right. What a lot of people, you see this this is not working. This is 0, this is 0. So it looks like the potential energy is equal to the kinetic energy. That's not always the case. I mean, people walk in, they see this first example, and the takeaway is usually this. This is not the usual case, right? This happens to be true here, only because the kinetic energy here is 0 and the potential energy here is 0. In general, this is not going to be 0, nor is this, right? In general, all four of these terms are going to be something other than 0. Okay. But in this case, 75,000 is equal to kinetic energy. So we know the kinetic energy is 75,000 joules. We can go on to the next problem, find the speed at x, right? We're still using the same 2 points, but for this problem, we're trying to find the speed. The previous problem, we wanted to find the kinetic energy. Now we want to find the speed, right? The difference being that instead of leaving it as KE, we would now write it as 75. 75, remember, is 1/2 m. So 1/2 m v squared, and now we solve for v. The velocity is then 31.62 meters per second, okay? So if you start from here, at the bottom, you're moving at 31.62 meters per second, assuming that there is no friction. Remember that this is less than 25. That's going to become important in a couple of minutes, okay? So we start from here. We start from rest here. At the bottom, it's going to be 31.62 meters per second, okay? All right, what about at y? Let's find the speed at y, okay? What's the speed at y? We do the same thing, right? We still have the same, here's the boxes from before. Right? I haven't changed anything here. There's the 3 boxes. But now what I want to do is compare the position at y with either w or x. I don't care which. I mean, we know both, right? But let's compare it to the initial w and y. Okay, so here we see specifically that, oops, what happened to this? Okay, I pushed the wrong button. There we go. All right, stop it. Stop it. All right, the potential energy here is not 0. In the previous problem, this was 0, right? That's not the case here. So 75,000 joules is the total energy at W. The total energy at W is 75,000. The total energy at Y is 30,000 plus 75 V squared, and you solve for V. V is 24.49 meters per second. Okay, simple enough. This was, again, for the case of no friction. Okay, so all we have is conservative forces acting. Okay, so let's take it on to the next complication. Let's suppose that that there is friction. Okay, so we'll use the conservation of total energy. This should say conservation of total energy right here rather than mechanical energy. So let me sort of correct that for you. So this says total energy. Okay, conservation of total energy equation, right? If it was simply this would be mechanical energy, but here we're adding energy lost and energy put in. Okay, but here, suppose that we now have friction. Suppose that the speed is 25 meters per second at the point X. Remember, it was 31 before, but now it's 25. So that means that some energy is being lost someplace. Where is it lost to? It's being lost to friction, right? We're not putting any energy in here. All right, we're just losing energy due to friction. All right, so how do we go about solving this problem? Exactly the same way. Okay. Again, we write down the information at the three boxes. Nothing's changed at W. Right. It's still not moving, and it's still the same height. At X, the potential energy is 0 because it's at the ground. But now we know the speed is 25. Right. So we know the kinetic energy at the bottom is 46,875 joules. And we do the same thing we did before. It's not that this box equals to this box. It's that this box here is what we started with. This is the mechanical energy we end up with, and the energy lost will be the difference between the two. So what we have is there's no energy input. That's 0. 75,000 is this box here is 75,000. At the bottom box is 46,000, right? So that's these two. Potential energy bottom is 0. Kinetic energy is 46,875. And then the energy lost to friction. Okay, so just subtracting 46,000 from both sides, we get the energy lost to friction is 28,125. Notice that's positive, right? The work done by friction will be the negative of that. Okay, I find it more satisfying to write the expression this way, with energy lost on the right side and energy put in on the left side. That just makes more sense to me. If you want to write it with as work done by friction, then you'd have to have a minus sign here, okay, to get that. Okay. All right, let's take it one step further and talk about the roller coaster. It's where did the roller coaster start? You didn't climb a ladder to get to the top of the roller coaster. The roller coaster starts at the bottom, right? And it's usually pulled up a straight ramp by some sort of cabling system, right? There's a motor that's attached to a pulley and pulls the roller coaster up. It gets to the top, and the roller coaster, once it gets to the top, very easily is released. And it's not moving very fast at the beginning. It just has enough speed to basically get from here to there. It moves very slowly, and then you get to the drop off, and you raise your hand and scream ah, and you go down. Okay, so the roller coaster is pulled by a cable from the ground to the point W. How much work was done by the cable on the car? Okay, again, this is, we don't know, and in fact we do know that it's not conservative, but we don't know if the force is conservative, so we have to use the so we have to work with the fact that it is a non-conservative force. So what do we have? Yeah. Okay. So what do we have here? Oops. Right here, I need to be able to draw. There we go. The potential energy here is equal to 0. The kinetic energy here is 0. The potential energy here is 75,000. And the kinetic energy here is 0. Right? And so what do we have? We have the energy input plus 0 plus 0, right? This are these two zeros. That's equal to 75,000 plus 0, 75,000 plus 0, plus the energy lost to friction. And, I didn't state that there was no friction, but there is no friction here. So there's no energy lost. Okay, and so therefore, the energy input by the cable to get the car from the ground to the top of the roller coaster is simply equal to 75,000 joules, which, by the way, is simply the potential energy at the top. That's where that potential energy comes from, right? How did we what is the work done? When we talked about potential energy, it was introduced as how much work do we have to do in order to get the thing to the top of the ramp, or the book to the top of the table, or the other way around, from the table to the floor. Okay, so it's simply the conservation of it's just simply the potential energy there. So that's where that's coming from. Okay, all right. So as a review of everything that we've just done. Conservation laws, when applicable, greatly add our analysis of physics problems, okay? When they're applicable, okay? Conservation of total energy is always valid, so it's always applicable, okay? It's just a question of how do we handle the energy lost and the energy input. When you're talking, by the way, of fundamental forces, all right, if we talk about forces between subatomic particles, there is no friction, for instance. Energy lost or energy input would be bonding energy. So that gives us an idea of the force that's acting between particles, for instance. Okay, but the forces that are valid are really conservative in nature. All right, and then you have conservation of total mechanical energy, so which is sometimes valid. It's valid when there's no non-conservative forces, basically for you guys when there's no friction. Okay, the work energy theorem is simply the conservation of total energy. Oops, is simply the conservation of total energy, but written in a different way. Okay, conservation of total energy and the work energy theorem are one and the same. Okay. Conservation of mechanical energy, total mechanical energy, is simply a subset of total energy when there is no non-conservative forces acting. Okay, so this is basically all of physics. What I would like to have done, if we had had the time to continue, is to take an example of, say, we can string different processes together, and this is where the fun really starts. Is you have, say, a block of wood here, and you shoot a bullet into the wood, or an arrow into the wood. What happens to the bullet? Say it embeds itself into the wood, and the wood rises to some sort of an angle here. Okay, and in this case, we would have this collision process that takes place, followed by conservation of energy process, where the pendulum swings upwards, right? And so we have this, and we could talk about how did this thing accelerate in the first place. So we could have another process there, but we take a complicated problem, we break it down into two separate problems that we can string together. Okay, and that's where the fun in physics begins. We've done so we've done all the introduction to physics, which to me is a lot of fun. But the fun really starts at this point, where we can start taking realistic problems, right, and looking at what we can do with those realistic problems. Okay, all right. So last homework, hurrah! Right, this would be due next Tuesday, the 25th. You have two homeworks. One is the Work Energy Quiz 2. It's something I used in the past. I didn't feel I was too lazy to change the name, and therefore I didn't have to write anything. Truth be told. All right, so this is you upload your solution to this quiz. All right, there are no quizzes this quarter. Upload upload this quiz to Classroom by next Tuesday. Then there's a second homework there, conservation of energy PowerPoint questions. I think there's 13 questions on the PowerPoint. The solutions are there. If we had another week, we can sort of play with these, and like I said, this is where the fun begins. But these are not the multi-step problems. These are simple one-step problems that we had before. They're kind of fun. The first half of them are about King Kong. But have some fun with them. I think there are 13 problems. They're very straightforward, and the solutions are there. And what you are to do for that, this is your extra credit assignment for this week. Do all 13 of those problems and then upload yes or no, indicating that you have completed or did not complete this assignment. Okay, I will trust you. So upload that when you're done. I hope that you have benefited from this. It seemed like you guys have been doing very well since we've been kicked out of school. To be sure, I am proud of the work that you guys have done. I would like to have those couple weeks back so we can actually bring this whole topic to its logical conclusion, where we take everything that we've learned and put it into basically one big problem or problems like that. Okay. I hope you have gotten something out of this, and enjoy your last homeworks. Stay safe. Have a great afternoon and evening.